Hey, what's up? We're just about to get started on the Day 8 challenge on Advent of Code. And I think this one's going to be really interesting, partly because we're going to approach it in two different ways. If you recall our strategy, often we want to make the code work first, then we want to make it more efficient, and then make it beautiful. Sometimes the kinds of changes we're making here when we go from step 1 to step 3 are more sort of the micro optimization style of changes. And this is going to be a really interesting one because we're actually going to come up with like two completely different solutions, at least for the second part here. So that'll be something to look forward to. It'll really sort of illustrate how reformulating our approach can really alter the efficiency of our solution. But anyway, I guess we should actually take a look at what the problem is asking us before we go any further. So this one, it seems to be quite a bit simpler than the previous challenge, which had us going over a lot of basic definitions at first. I don't think we're going to have to go through as much before we actually dive in here. This should be a lot simpler. I don't think we'll have as many like applications of graphs or search algorithms. Or will we? I guess we'll find out. Anyway, this is one that's about a handheld game console. They provide a nice link to the Wikipedia article on that, just in case we're unfamiliar. Very considerate. And basically, we're given a list of operations. It's kind of like we're given... I was about to say we're given like a list of code, but that's getting a bit meta, right? So basically the idea is we're given this list and it's just three different types of instructions that we can do here. So basically we have an accumulator value that starts at 0. And if we see like an ACC, then +1 or minus whatever, we're going to increase the value by that amount. If we see something that's JMP, that stands for jump, and that means that we're going to skip from here to basically the operation or the instruction that's 4 down from here. Whereas normally if we just run like an ACC instruction, we'll just resume from the next instruction after that. And then the only other type is this nope, which basically we don't do anything. We just kind of skip over this. At least for part 1, we're going to skip over this and not do anything with it. And just move on to the next instruction afterwards. Okay, so the question that we're being asked is basically when this code completes, what's going to be the value of the accumulator? And I should say, it's not actually going to complete. What it's actually going to do is basically repeat an instruction, or it's going to reach an instruction that it's already seen. So if we take a look at the example over here, we start with a nope operation. Nothing's going to happen there. Accumulator +1, so we're going to increase the value of the accumulator, so now it's 1. And we move on to the next operation. This says jump +4, so we go all the way down to this operation down here, accumulator +1, so now the accumulator is going to be 2. We'll move on to the next operation, or the next instruction, I should say. This one says go back 4, so we'll go to the ACC +3. The accumulator will now have a value of 5. It was 2 before, we've added 3, so now it's going to be 5. We'll move on to the next instruction. This tells us to go back 3. We end up over here again, and we've actually seen this instruction before. So we're going to stop the code at that point, and our accumulator had a value of 5 at that moment. So basically that's what we want to return in this case. So when we do get to a point where we've repeated an instruction, or we've encountered an instruction we've already seen before, we want to stop the code. Okay, so basically I want to go through this in the simplest possible way to begin with, so I'm not going to worry about making this code super functional or anything like that. We're just going to have an accumulator, we're going to have an index. For our sample over here, let's say, I'm just putting this in case we decide to do the fetch code stuff like we've done before. Anyway, so we'll say const instructions, and we'll make it response text.split on the new line character. Oh, and I guess we don't want to forget to do our .trim as well, always an important thing, so that we don't end up getting an extra empty array element from there being a white space character at the beginning or end of this thing. Okay, cool. So we've got our instructions, and now basically what we want to do is for each one of these instructions, so for const instruction of instructions. Basically, we want to go in here and say, like for each one of these things, process it, right? So whether it's ACC, JMP, or NOP, we need to process it in the appropriate way. So let's actually do full screen on the IDE over here, and let's go through this. So for the first instruction, I guess we're going to do a regular expression, right? I mean, that's become pretty common. So let's go ahead and create one of these. So what do we want our regular expression to look like? Well, let's take a look at what the instructions tend to look like. So basically, the first thing that we want to get, and we want to capture this, so we'll use parentheses to open up a capture group. It's basically going to be ACC, or it's going to be JMP, or it's going to be NOP, and that's it. So that one's pretty straightforward. Okay, what else? So after that, we have a space. And then we have a plus or minus sign. And then we have some number of digits. Maybe more than one, maybe not, but we have a number, right? This one has 2 digits, so we're keeping that in mind. And then notice I'm putting the plus minus thing as part of the capture group. I want to actually get the full number, not just like the digital part of it, right? But the sign of it as well. And the reason is because if we take something like this, like +1, and we do a parse int on that, it's just going to be 1. If we take something like this, -99, and we do a parse int, it'll be -99. So it's going to maintain the sign over here. We could bust this out as like its own thing and then use some sort of conditional to decide whether the result should be positive or negative, but we don't have to, so we might as well not. Okay, so basically the idea is that we're gonna get 2 capture groups from this, or we're gonna capture 2 things from this, right? We're gonna get the type of instruction, and we're gonna get the amount of the instruction, or the amount corresponding to the instruction. So that's basically either how much we're gonna increment the accumulator by, or it's how much we're gonna increment the index by. Okay, so basically recall when we do one of these things and we do a dot match, which is what I'm just about to do. So I'm gonna say instruction dot match. So keep in mind, this thing is a regular expression, which is basically like a miniature programming language. We can use this in a lot of different languages. And in terms of using it in JavaScript, we have some built-ins. So we have the dot match built in, which is for strings. We also have like dot test, which is a built-in for regular expressions, but we don't need to get into that right now. The idea is that we can just assume that anything we see in our sample or in our response text is going to be sort of this form, so we don't need to test against it. If we were concerned that it might not be, we might want to include test, but we won't worry about that. I'll just write this out in full for now. So full match is the first thing we're going to get. So yeah, sorry, I'm kind of doing 2 things at once. When we do instruction.match, we're going to get an array coming out of this. The number of things in that array depends on how many capture groups we have within the regular expression. So we're always going to get one thing, which is basically just the full match over here, and then basically one additional thing for every capture group. So we should expect 3 things here. And they go in order. So basically left to right, the first capture group we see is the type of instruction, and then it's the number or the amount. I'm going to say num string here just to remind ourselves semantically that this thing is actually a string and that we'll need to do a parse int on that. And then another sort of visual semantic reminder is I'm going to replace full match with just an underscore character. And the reason behind that is because I don't intend to use the full match at any point. You might ask like, well, why not just not include it? And the problem with that is like, it's part of this. This thing is itself an array, you know, like if I had 2, 3, and 7 in here, there's a difference between having it like this and not having this, right? In this case, the underscore would be 2, type would be 3, and numstring would be 7. Whereas if we do something like this, type would be 2, numstring would be 3, and nothing would actually end up with the value of 7. So basically, we do need to have something in there just because of the way destructuring works in terms of arrays, but we're not actually going to use it, so I'm just using underscore as kind of a placeholder here. Okay, so we can continue from here. Basically, for each of these instructions, we've got the type of instruction and we've got the num string. Let's actually get the num by doing parse int on our num string. Okay, cool. So now we've got the type and the number, and we can basically just perform the corresponding operation. So I'll just say if type is ACC first of all, then in that case, we're going to increase the accumulator by the amount, or by the num. And then we're also going to increase the index by 1. So we can just do plus plus for that since it's 1. Okay, else we should probably check if the type is a jump. JMP. Okay, so if it's that, then we basically just want to say index plus equals whatever the num was. All right, and that's it. We don't need to worry about the accumulator. And then do we need to do anything if it's a nope? Well, yeah, we kind of do. So basically, and I'm actually noticing something now. This type of loop is not actually going to work. This type of loop is basically just going to go through every instruction. And we don't want to go through every instruction here necessarily, right? We want to go to the instruction at the current index value, whatever that happens to be. So that's why I want to put in here, if it is a nope type, then we're at least going to get an index plus plus. So we shouldn't have a for loop here. What we should actually have is a while loop, something that's just the condition part of it. It's kind of like the middle of the three things in a for loop. So what we want to say is while index, I was about to say while index is less than the instructions.length, but that's not actually what we're trying to do here. What we're trying to do is to keep this going until we find something that we've already visited. So I'm going to make a new set, and basically we'll just say while the current thing has not been visited. So while not visited.has the current index, and we'll just put in the index basically as soon as we visit it. In fact, let's just put it right here. So we'll just say visited.add index. So that the next time we encounter this thing, it'll already be in that set, and it'll be like, oh, we're not going to continue that loop. Okay, so then basically we'll do this while loop, and eventually this will end. And then when it does end, we'll just return the value of the accumulator. Okay, cool. And maybe we should like wrap this all up in a nice function. That would be good. Okay, cool. So we'll make this a function. We'll just call it run program. And should it take anything in? Yeah, let's just give it instructions. Okay, we'll give it the instructions as its argument. Okay, or parameter. Anyway, okay, so let's run this now. Yeah, I guess I should probably actually console log something, and I should probably actually run this function too. Geez, 2 reasons why we weren't seeing anything that time. Okay, run program and then instructions. Let's try that. What are we going to get from that? Well, we're going to get a big old error. Why is that? Because we're saying instruction.match, and we don't actually have instruction anymore. So what is instruction? It's basically what we would get at the instructions array at index. And actually, I'm now realizing there's only one time we need to even reference that. So I'm just going to put it directly in here. Instructions at index. That's really what we're talking about. If we had to use the variable instruction a whole bunch of times, I would consider, keeping it as a variable. But I think this is fine since we only need it once. Okay, so now let's run this. Hey, we get 5. Okay, great. So if we want to revisit what we had over here, that was the value we were looking for. It was 5. Okay, cool. So we could probably, with some degree of confidence, pop in our actual input, not just the sample, and then run that and see what we get and return that value. But I think we should try to make this functional. I had such a fun time in the day 7 challenge converting everything to functional. I think this it would be a treat. Okay, so basically here's what we want to do. For run program right now, basically like everything inside of this is not really functional at all, right? Like we're starting with these lets. This should be a dead giveaway. The fact that we're actually reassigning these is really not very immutable of us. So it's not really following with the functional programming paradigm. So we want something that's going to be like this. I think the first thing I'm actually going to do is just to avoid the kind of awkwardness that tends to come with like the regular expression stuff. Like if you think about it, like I'm kind of reassigning this, like we're just saying, okay, now we have this new regular expression. It's not like it has a name, so we're just putting this in here, and then basically we're processing that, and then we'll process it again. Like we might return to this instruction later. We don't necessarily want to have to process it again when we see it again. Okay, so basically what I want to do is for the instructions, I want to put a little more pre-processing into this. So I'm going to say a .map, and this map will have, an instruction, what we were calling an instruction before. So something like this. And what we want to actually map it to is something a little closer to like what we would get after doing this kind of stuff, just so that we don't have to include it in our run program function. It's kind of like a separation of concerns sort of thing. Okay, so basically for each instruction, we'll just bring this back to what it was. Yeah, so instruction.match type num string, we'll get the num from that. And then what I'll just do is return an object that just contains type and num. Now, I think we saw this in a previous video. If ever you see this where it's like, whoa, that's weird, you're making an object, but you're kind of like, it's not like you're saying what the key is and then, the value after that. So if you ever see this, basically what it means is literally like it's going to say type, like the name of the variable as the key, and then the value of the variable is like whatever the value of the actual type variable is, So maybe it's going to be like the string ACC or something like that. And then num will be whatever that is, maybe it's 1. Okay, cool. So basically that's the idea. I'm pre-processing this so that instructions is actually now an array that contains objects that have just two properties, type and num. Okay, so with that in mind, now we've got this thing, we're taking in instructions. It looks like we're not using instructions right now, which is kind of not ideal. So basically it's at this point with the index that we actually want to put these things in. So we can use destructuring and say, well, we've got an object that consists of a type and a num, and that's what we're going to get when we actually look for our instructions. Instructions at index. Because this thing is an object and it contains a type and a num. Now we use destructuring to extract that type and num. So each of these is going to be its own constant, which we can then use later on here. So this really hasn't helped in terms of making this more functional, but well, maybe it has. I don't know. All I'm trying to say is we're not there yet. Okay, so basically now instructions is this nicer thing. We don't have to worry about like going through and doing a regular expression match with it. We don't have to worry about capture groups and that kind of stuff, but we still have to do something about this loop. It's not ideal. It's not ideal that this thing is in a loop. So here's what we want to do. Basically, we'll just do these one at a time. I'm going to say run program. I'm just going to make a new one of these, I guess. Instructions. Yeah, instructions. We'll put that in there, and then basically the function itself as inputs will have like all of these values. Okay, so this is actually, yeah, I'm glad we're talking about this. Excuse me. I'm glad we're talking about this. So in terms of functional programming, there are kind of like tricks that we can use in order to convert something from a loop into a recursive function. So basically, all of these kinds of initial conditions, things that we're doing before the loop here, we're probably going to insert those somewhere here. Okay, they're going to be like our initial values of the variable. So I usually like to slip these in as optional variables, so ones that have default values already. So I'm just going to put each of these in, and we'll even put visited and like declare and assign this new set right in the function header. Nothing wrong with that. And then basically the idea is we'll do something like, we'll check this. We'll check to see if visited has the index. We'll see what happens. I'll basically just say if visited has the index, then just return whatever the value of the accumulator is right now. Okay. We'll deal with this in just a sec in our in our quest to make this more functional. But anyway, the main thing is the loop itself, like the thing that's actually looping. This is where we'll do another function call. Okay, so we'll want to know what this stuff is. Yeah, this is important. And yeah, we'll probably want to do this as well. So, okay, good. Yeah, we'll include both of those. So we're adding this to the visited. Well, yeah, we'll see if we end up keeping that, but spoiler alert, we won't, because .add is not really an immutable thing. So, okay, we'll get our type and num from instructions at index. Okay, that's good. And yeah, I like the idea of passing in the instructions array here. This is a bit different from some of the recursive functions we've done before. But anyway, we've got our type, we've got our num. We can basically just do something like this if thing. And then instead of like changing these values, what we'll actually do is we'll return the result of calling this program with the same instructions array with accumulator plus num and with index plus 1 and with this same visited thing, since we've added our thing to the list already, or to the set, I should say. Okay, and as I said, that might end up changing, but we'll see. So basically, this is all I wanted to sort of show, is the idea that instead of like, modifying these values here, we're just making kind of new values out of them, so that the next time we call this function, it's kind of like a new iteration of the loop, right? Like the index has gone up a little bit, and the accumulator is a new value now. So everyone's very happy. Okay, so in this case, we want to increase the index by num. So we'll say index plus num, but the accumulator will remain the same as it was. So we'll just pass that directly in there. And then finally, this one, we're only increasing the index by 1, and we're doing nothing to the accumulator. Okay, so that's our run program. And let's just go ahead and delete this one for now, just to see if this actually works. Now, as I've said before, the fact that it kind of rearranged this, first of all, that's because I'm using a VS Code extension called Prettier. It's very good. It does the kind of the stuff that I don't want to in terms of making the code look visually nicer, making it consistently indented and stuff like that, which is, not to be overlooked. That's an important part of writing nice, clean code, because somebody's got to look at this conceivably, right? Okay, so the reason I say it's a good sign when we see that rearrange is because it wouldn't do that if there was a syntax error in the code. So, we can sort of rest assured that it's probably not too bad. Okay, so here's what we want to do. Since there's a return on every case here, like no matter what we do, we're going to return something. So what we're going to return is going to depend on what the type is. So if the type is ACC, then we're going to do this run program thing. And otherwise, we need to ask ourselves, okay, well, it was an ACC, but was it JMP? And if that's the case, then the thing we want to return is this. And if that's not the case, then the thing we want to return is this down here. And this is getting way out of hand. I mean, like, yeah, we don't want all this on a single line. That's unruly, so we're going to save that and go all the way back to the left. And yeah, that's a little nicer, not bad. Okay, so I can maybe get behind this. I don't know, something about this if is sort of rubbing me the wrong way. And in fact, something about this, yeah, we kind of talked about this before, the idea of adding the index here. So here's what I want to do to modify this. Instead of adding the index to the set, let's do it a little more directly than that. So we could say that this now, in fact, here, let's just say next visited. Next visited is going to be a new set. And what's going to be in this set? Basically, it's going to come from the contents of whatever was already in visited, but then also it's going to have this current index. So this is just a way of adding this onto our set, or actually, no, I shouldn't say that. It's a way of creating a new set that's basically what would be the result of just adding this onto a set. And this way, it's just a little more immutable. It's a little more in line with the functional programming paradigm, and so we like it. Okay, cool. So basically, the only issue I have now is this. And there's actually kind of a nice thing about this, because before we were saying, well, first we have to check if visited has the index, right? And then we can add index to visited. But now we're not adding it to visited. We're making this new set. So we can actually just check this. We can say, well, hey, this, visited.has index. And if that's the case, return accumulator. Okay. Otherwise, return the rest of that stuff. Okay, so we're going to save that and we'll run it, and it's still working. So that's pretty good. Nice stuff. Now, I think we could probably even drop the accumulator thing from this and do it sort of like in the reverse direction. So instead of doing it like this, I could say that the thing we're returning will be the accumulator, in which case we don't need to track it all the way down. We could basically just get to the end here and say, yeah, just return 0, right? And then instead of like accumulator plus num, we would then say num plus this, because this is the thing we're returning, and that's where we should actually include that. So yeah, we could actually take the accumulator out of this entirely, I think. We'll see. Yeah, it turns out we can. So it's really up to you. I mean, you might decide that this is a bit cleaner to do it this way. I think that's what I'm deciding. Technically, we could also get rid of the instructions, because that's like just the same every time. But this is, I'm not totally sure if we should be comfortable with that, because like we otherwise would be sort of reaching outside of what could be considered the scope of this function. So the fact that this is situated in the same location, the same namespace where instructions is defined, means we're probably safe to not include it here, but oh well, it's fine to have it. I mean, like, unless it's really bothering you. But yeah, like, I guess all I'm trying to say is, like, if we really wanted to, we could actually just get rid of instructions entirely from all these calls here, and then we wouldn't even need to put it in here. We could just say run program and then run this, and like it'll still be totally fine. So it's up to you. I'm going to leave it in for now, just for fun. But yeah, I think we're kind of reaching a point where we might want to actually just take this stuff and use it to answer the question. So let's do that. So I'm going to go over to my fetch code, and I'm going to grab this stuff, and this time I'm going to put it in here. So response text is going to be this. And now we should be able to just take this and all of this, I think. Let's just make sure we have the right day. Yeah, day 8 looks good. So we'll open up our browser console on the split screen over here, and we'll just paste in the code. So this code is basically going to use the fetch API to just directly grab whatever the puzzle input is. So this way we don't even need to look at it. We can solve the problem without even knowing what the input was. And then basically the rest of this is just the code we were just working on. So that's why it looks so nice and functional. Okay, so 1939. Let's see if that's our answer. Yeah, okay, nice. Looks like we were correct. So we can go ahead and move on and see what part 2 is asking about. Okay, so this is where things get really interesting. So basically what we find is there was a reason, in case you were wondering why this nope thing was in here at all, and especially in case you were wondering why they would bother including like a number next to it. Basically, it's because there is a problem in the code. So we're saying exactly one of the lines here, exactly one of them has been corrupted. It was either a NOP that was supposed to be a JMP, or it's a JMP that was supposed to be a NOP. So, or nope. Anyway, the point is, we need to find a way to figure out like which one that was, and then find the actual correct answer. So the hint they've given us is that the code actually is supposed to stop. We actually are supposed to reach a point where we get to the end, where it's like not just like a repeated line that we end up. It's not that we like find a repeated instruction. I forget which one it was before, but anyway, it's not that we find a repeated instruction. It's that we actually reach the end of the code. So we should have like index equal to instructions.length in this case. Okay, so they give us this example, and now they say if we were to switch over the JMP to an NOP, so now this is no longer going to send us back 4 lines. It's going to allow us to just sort of continue within the program, continue the instructions. That would allow us to reach the end, and then we would have a value of 6 on the accumulator by the time we reach it. Okay, so that's basically our goal here. And I have to say, I mean, beautifully constructed challenge. This is really some nice stuff, partly because of what it's going to illustrate a little later on, but I don't want to give any spoilers related to that. The main thing is that let's come up with a strategy, okay? So we know, just going back to our full screen mode here, getting our sample back in the mix, we know that one of the ones that says JMP or NOP, so out of the 4 possibilities here, one of them is corrupted. And it should be the other thing. And we also know that it's exactly one of these things. So that's going to be helpful information. And we know that we can tell which one is the actual one because it's actually going to reach the end of the code. Okay, so like for example here I'm asking, hey, does visited have this index? When really what we should be asking, or what we will eventually be able to ask is, did it reach the end? You know, like is index actually at the end now? Okay, so basically we're not just going to run the program. What we're going to do, this is our game plan, okay? And this might seem a little brute force, because remember, we've got to make it work first, right? And then we'll talk about making it efficient and making it beautiful. Okay, so what we want to do is basically consider all the possible corrected instructions. So what do I mean by that? Well, more specifically, for any NOP or JMP instruction, try the program with the opposite type. Or yeah, with this instruction as the opposite type. That's more what I mean. Okay, so basically there are going to be 2 parts to this. We're going to come up with a list of all the possible corrected instructions, and then we're going to go through that list and see which one actually has a successful run of the program. And that's going to be all there is to it, I think. So basically, let's see. Yes, okay. I'm sort of realizing now we may want to go back to including the accumulator in here for reasons we'll find out eventually. But, yeah, I think that might be good. The reason I say that is because we need some way of telling, based on what the function is returning, we need some way of telling if it actually reached the end or if it actually just encountered another instruction that it had seen before. So let's take this and let's get it back in here. We missed you, accumulator. I don't know what we were thinking, getting rid of you. Okay, so we want to add num to this and delete it from this over here. And then there was a console log that we were doing before, console log of run program with instructions as our input. We'll save and run that. And now we're getting a 0. Yeah, because this is 0. This should be the accumulator. Okay, there we go. So we're getting 5 now. So everyone's happy again. Okay, cool. So we'll get rid of the console log. No one wants to see that. We'll go through all the possible corrected instructions. Okay, so how are we going to get those? Yeah, good question. So here's what we'll do. Okay, here's what we're going to do. We're going to just do something like this. Const candidates is going to be an empty array, and then we'll go through the list here. We'll say for let I be assigned the value of 0, I is less than instructions dot length I plus plus, and then we'll just say const type and num. Type and num. We probably don't need to know the num. We could probably just say type is assign the value of instructions at I. Okay, And then basically what we want to do for this is check if the type is one of the applicable ones. So if type is, what were they called again? ACC? No, that's the one that's fine. So if it's NOP, then we'll say something like this. Const new instructions is going to be a copy of instructions, with the added caveat that new instructions at I is going to be assign the value of the old instructions at I, but with a dot replace on it. Yeah, wait a sec. That's not true, because I just remembered. These aren't strings anymore. We don't have to do a dot replace on this thing. We already have these as like type num objects. So I'm just going to say, yeah, actually even better. We'll just say this new instructions at I at type. Hold on a sec. I'm just thinking if we do this and change the type to JMP, that might not be deep enough, in the sense that this might alter this object for like future runs of this code. So we shouldn't actually do it that way. We should just say new instructions at I is assign the value of, yeah, a new object consisting of instructions at I. Or yeah, you know what would be easier? Just actually taking the num from this thing and then saying, I want the type to be JMP and with the same num, whatever it was. Okay, that's better. Yeah, because it's a new object now. Not that, we're being terribly concerned with doing this functionally, clearly, at this point. Okay, so new instructions is that. And then we'll just say, like, yeah, console log of run program with the new instructions. Yeah, let's try that. Okay. Syntax error. So what's wrong with this? Oh, yeah. It still needs to be called type. Okay. So, yeah, I was sort of used to the way we were doing it over here, so it didn't know that this thing was called type. We've got to specify that. It is an object after all. So it doesn't know. Okay. Yeah, so we're getting 0. Which is, I don't know if that's surprising or what. Oh, yeah. Okay, so the reason we're getting 0 is because we're changing this nop into a JMP. It's saying jump 0, so it's just instantly going into that infinite loop, and it's just saying, okay, well, we never bothered to increase our accumulator. We're at an index we've seen before, so that's the end here. Okay, so what we do want to do now is, instead of returning the accumulator, what I want to say is, if it doesn't complete, just return -1, okay? And then otherwise, if it does complete, this is where we actually now want to check, did it get to the end? So we could say, is the index equal to the final index, which is instructions.length? Okay, if it's equal to that, then that means it actually it reached the end, so we can actually return accumulator. Otherwise, we'll return the rest of this stuff. Okay, and was there anything else I was gonna change? I feel like I forgot something, but I the evidence will be in the output here. So yeah, okay. I guess the other thing I wanted to do was basically just say just else on this thing, if the type is JMP to begin with, now we're going to change it to NOP. Okay, so let's try that. And then we should expect that this is going to fire 4 times. We should get 4 console logs because we have 1 NOP and 3 JMPs. And hopefully one of those is going to not be -1. In fact, we should really hope that exactly one of them is not going to be -1, because if they were all -1, it means this isn't working, we're not reaching the end of the code. And if more than one of them is not -1, then that would actually mean that there isn't a single unique instruction for us to modify, which would be bad too, because that would mean, well, like we kind of need a unique value. Otherwise, how are we going to know what to type in the as our answer, right? So taking a look at this, what's the most recent thing here? Yeah, okay, so we had -1, -1, -1, and then we get to this point where it's like you're asking for type and num of this thing that's undefined. There is no instructions at index. If if index is already greater than the largest possible index we can use in instructions. Because remember, like the index is 0 based, so we can't use instructions.length. We could instructions.length -1 would be the largest index we can use for a 0 based array like this. Okay, so going back to this, basically the idea is we need to deal with the case where this thing is undefined, because that might happen. And in fact, it's kind of necessary because we need to get to this point, because this is where we're doing our return. And, you know, like we're checking this afterwards, right? And we've already done the destructuring at that point. So anyway, I'm just going to do the same thing we did in video 7. So I'm just going to say, if this thing is undefined, we'll use the Boolean OR operator to typecast this into a false. And of course, if it's an OR, then like in order for it to be true, it only needs one of the two statements to be true. So if this thing's true, it's not going to bother looking at the next thing. The next thing is just going to be, let's see, what are type and num supposed to be? Well, I'm just going to make it an empty object. So this way, type and num will be undefined. Like these are not going to have a value. But at least it's not as bad as this thing being undefined and us trying to get some sort of destructured properties out of it. That's what leads to this type of error happening, right? So we won't be able to use type and num, but we shouldn't have to, because like it should get caught by this ternary right here, and we should return the accumulator in that case. Hey, there we go. So check it out, -1, -1, -1, and then we get 8. So 8 should be the value that we get from this. Yeah. And just looking at the split screen code here, the problem description, basically, yeah, 8 is the expected result. So nice. We could actually go ahead and submit this now, I guess. But there's just one problem. I hate it. No, sorry, I shouldn't be so negative. It's great, and I'm glad it's getting us the result we're looking for, but this feels so brute force to me that I would just say it's downright sloppy. Okay, so basically, I don't want to do it this way. I don't like the idea of like looking at all of the wrong things and like fully processing them until they get to a point where they're not working. It just feels a bit inelegant. So I really want to talk about a more efficient way we could solve this problem. And like I was saying at the start of the video, I don't mean just like a superficially more efficient way. I don't mean like a micro optimization, like, oh, you know, if you use a dot map instead of a dot for each, it actually goes a little faster. Like, I'm not talking about that. I'm talking about like a radically different way of solving this. Okay, so what I want to do is, first things first, you know, I kind of just want to delete all this. I don't want the console logs to fire. I'll just comment those out for now. The reason is because I want to get this stuff on screen, and I kind of want to see it with its here's what I want to see. Okay, I'm gonna say object.entries because I want to see the indices of these things as well. So object.entries is kind of like doing object.keys or like that type of thing. And you might be thinking, well, but sample's not really an object, is it? Or, you know, response text, I guess I'll just call it that. And we'll do the dot trim and the dot split on this thing. So basically, you make a good point. Even after we split this thing on the new line characters, it's basically just an array of strings. So the idea of doing object.entries on an array of strings feels kind of strange, but an array is a type of object. And we talked about this before in a previous video, how in an array, like the keys are just numbers, right? So we could do something like this. We can look at our object.entries for something that's not an object in the conventional way we think about them, it's still going to work. So we've got all of these laid out. Now, the reason I wanted to do this is because I want to think about another way we can solve this problem. And I'm going to use the whiteboard to solve this. So basically, let's think about how we can go through this problem. So I just wanted to have the instructions listed out here so that we can just sort of refer to them in terms of their indices, as opposed to having to go through like their actual instruction, right? So assuming this code is correct, instruction 0, oh, whoops, I'm not on the right tool. Okay, my mistake. So, all right, we start with instruction 0. There we go, 0. Okay, instruction 0 just says nope. So it takes us to the next instruction, which is instruction 1. And that says accumulator plus 1. And then we just move on to the next thing over here. So this takes us to instruction number 2. Instruction 2 says JMP plus 4. Okay, nice. Starting to finally get a more interesting thing here. So that takes us all the way to instruction number 6. And then basically we follow this, and instruction number 6 tells us to go to 7. 7 tells us to go back 4. Et cetera, right? We're going to reach the end of this eventually. And if you think about how we're going through it, like it's essentially just, it's a linked list, right? Like we talked about graphs last time. This is about the simplest type of graph we can get. It's just a linked list. So now I want to talk about another way we can think about this. And this is thinking about it in terms of there being a mistake in the code somewhere, or in the instructions somewhere. So this first one, or this 0th one, I should say, is a nope, which means we could treat it like a nope and say, okay, go to 1, do nothing else and just go to instruction 1. Or we could treat it like a jump, right? Because maybe this is the one that's wrong. So if it's wrong, then we're just going to jump 0, which brings us back to 0. So we're going to stop there anyway. And then, we'll look at like instruction 1 just takes us to instruction 2, and instruction 2. Well, instruction 2 is a jump. So we could say treat it like a jump and take us right to instruction 6, or treat this as though it's the one with a mistake in it. And then this will take us to just the next one, right? Just instruction 3, because it's a nope now, right? So it doesn't matter that there's a plus 4 after it. Instruction 3 takes us to instruction 4, and because it's just an ACC, so it doesn't matter. It couldn't possibly be the mistake anyway. So then number 4 is a JMP type, right? So maybe this one is the mistake, right? Maybe we've got 2 possibilities here. And actually, it turns out we don't. Not in this case. Why not? Because this came from a branch that already identified the mistake. Okay, so we're already on a branch that's assumed that instruction 2 was the mistake. There can't be more than one mistake, so we're not going to branch off any further if we've already found the mistake. So this is really interesting, right? We started this problem and we were like, oh man, it's a nice relief compared to the last one. We're not going to have to deal with any like graphs or search algorithms or anything like that. And well, surprise! So we actually are going to do a search algorithm in this case, kind of like that depth first search algorithm that we did before. So basically, that's how we're going to go through our instructions now. So yeah, I think I'm going to scrap this. I think I'm going to get rid of this stuff. I'm no longer happy with it. Now, in terms of this, I think what we'll do is just run like maybe a modified version of this thing. It's tough. Yeah, maybe we'll do a modified version of this thing. Maybe we'll just start over, actually. Let's just do a new thing. So we'll say const, what should we call it? We'll call this one, okay, we're going to call this one run command. And this is just going to be like, yeah, it's going to run a single command at a time. right? Just like that tree we were looking at. We're going to run a command, and then we're going to maybe take a look at this and maybe take a look at this. And like, remember, if it doesn't work, like in this case, we'll return at this point, and we'll return -1. Okay, so this one will return -1. And then this one down here will also eventually return -1 because we know that it's going to loop. Or no, sorry, that's not true. This is the one that is going to return -1. There actually is a branch down here that will be the correct one because we know this is not the one that actually has the mistake. So basically all I'm trying to say is like, if we're at a fork in the road, if we're at like a crossroad like this, right? And we want to know, well, which one is it? Since one of them is going to be -1 and then the other one's going to return whatever the accumulator value was at the time, and I think that's going to necessarily be a positive number, basically we can just say, well, take math.max, right? If it turns out the accumulator is not a positive number and we can't make that assumption, then we can adjust that. We can make this like -1 billion or something like that. But anyway, the point is we're going to use a math.max on these two possibilities in order to figure out which one is the correct one. Okay, so basically we're going to have run command. It's going to have an index, which is going to start at 0. We're going to have the accumulator value because we may need to know that in the case that we actually reach the end. We'll have a visited, which is going to be, just a new set to begin with. And we're actually going to have a new variable here as well called found mistake. Okay, and this is going to start out as false. So if you're wondering what this represents, and I realize I'm kind of getting off the screen here, sorry about that. Found mistake is related to this idea we talked about over here. The reason we didn't look at this branch because we had already found the erroneous instruction, right? So it wouldn't make sense to consider another one being wrong because we were told in the problem description that only one of them is going to be wrong. Okay, great. So we've got our things here. This is all set up to go. So basically what we want to check here is, well, first of all, let's just get the same stuff we had before. Type and num, we're just going to get directly from our instructions. It's going to be instructions at index, and then this is going to be possibly an empty object, just in case the index is out of bounds here, right? We want to make sure the destructuring isn't going to break in that case. I guess I didn't need to put these in parentheses. It's kind of awkward now. Anyway, okay, so we'll do next visited, same as before, which was a new set that we got from basically doing the union of whatever visited was before, and then a set containing only the current index. So now it's all together in this next visited, and we can also ask ourselves about like, should we go right for return? I don't know, that feels a little scary. We'll do the ifs like we were doing before. So we'll say if type is, I guess we'll start with ACC because now that's going to be the most straightforward one, I think. If type is ACC, then basically we're just going to return run command with index +1, accumulator plus num, next visited, and found mistake. So notice I'm not saying whether this is true or false because like we don't know what happened before this, right? We're not finding the mistake here, but it might have already been true from a previous thing that happened. Okay, so then we'll say if type is, what else is there? JMP, yeah, that's another possibility. In that case, well, actually, hold on. I don't want to rush into the return quite yet. Basically, what we'll do is ask ourselves if we found the mistake yet. So if we've already found the mistake, then it's pretty straightforward what we have to do. It's just going to be run command with index plus whatever the num was, accumulator same value, next visited as our set, and then found mistake is going to be found mistake, which we actually kind of know is true in this case. So I could just put true, but I kind of prefer this just in case, you know, what if somehow we made it in here? Anyway, okay, so basically that, and then if we haven't found the mistake, this is where things get interesting. So what we need to return is math.max of these two possibilities. So basically the actual, like the usual not mistaken run command, and the run command we would have if it was mistakenly actually supposed to be an NOP command. Now keep in mind, NOP is just going to increase the index, not change the accumulator, so this stuff is fine, but found mistake actually now has to be true, because like I'm saying this one was the mistake, right? So like if we're going to continue down that branch where we've already identified a mistake, we can no longer branch out any further, okay? So that's, I'm glad we're checking that. So, okay. That's going to be true. And where are we in here? Okay, yeah, great. And then else. Well, this one's actually going to be really similar. So it's going to be like this, except this is going to be a +1, this is going to be a +1, and this is going to be a +num. Because the difference is basically that instead of just moving on to the next instruction, we're going to jump to the instruction at whatever index we would get to if we added num to it. Okay, great. And of course that implies a mistake has been made because this thing was supposed to be an NOP, but we're treating it like a JMP. Okay, I want to get rid of that console log that we had before, just before I forget to do that. Okay, cool. So this is run command, and we've got some returns. I think there's another if thing that we've forgotten to do. So if the index is equal to instructions.length, first of all, then in that case, we should return the accumulator. And otherwise, if visited.has index, then in this case, we should return -1. Just, you know, go back, we're done. Okay, cool. So that would be an example, by the way, of what we saw right here. So that's our -1. Okay, cool. That's getting really messy. Sorry about that. Okay, returning to this. So we saved it. It beautified it. Is it going to work? Let's find out. So run command, console log. We want to run command. Do we need any arguments? No, it doesn't look like it, eh? All of these have optional values that are supplied, or default values, I should say. So we're not going to have to do anything to that. We'll run this, and yeah, we get 8. That was the value, right? That's what we were looking for. It's just a lot cleaner now than it was before. So here there was like, yeah, a lot of other stuff, a lot of other junk. Anyway, okay, so this is good. Could it be better? Well, yeah, of course. We can make it more functional. So basically, the only problem with this right now, the only thing that's making it not functional is there's a whole bunch of ifs. Aside from that, it's pretty good. Like we're not using loops. We're using a recursive function. And something to note about that recursive function, by the way, just before I forget, is we're no longer passing in instructions. It's kind of like I was saying before. We don't need to include that if we don't want to. We could put it in there, but I mean, that would be like, we're calling this like 6 times now or something. Like that would be a lot of extra instruction to include in there. So yeah, I think I'm okay to not. Part of the reason I wanted to keep it in this one was so that we could actually use that more brute forcing method where we did put in different arrays for instructions. But anyway, returning to this down here, the part I want to talk about, the part that's making me a bit uncomfortable, or the most uncomfortable, I guess I should say, is this. What do I dislike about this? Well, it's the fact that this thing is appearing here and here. Okay, there's a mantra in programming. It's DRY. Don't repeat yourself. Okay, so we want to keep this nice and dry. We don't want to repeat ourselves. There's a way we can do that. So basically what we can say is instead of saying like if found mistake and do this and then otherwise do the math.max, like we could just do the math.max anyway, right? And then just say like, oh, and by the way, like if it's found mistake, just disregard this one. Don't even bother with it. So we could do something like this where we say, well, hey, found mistake? Found mistake? Did you find it? Because if you've already found the mistake, just -1. Like, you shouldn't even bother checking this. So, you know, whoops. Yeah, I got my spacing all wrong. Yeah, so basically for this, it's just going to say, well, if found mistake, if you've already found the mistake, this is just a -1. So the math.max is going to default to this one anyway. Okay, so it's the same as just disregarding this. Okay, so because of that, we don't need this extra if, which, I mean, to me, that's a big savings. Look at that. This looks so much less awkward than the stuff below it. It's downstairs neighbor. So let's treat this one to the same modification. Found mistake, or found mistake, I should say. There we go. Okay, so let's just make sure this is still working before we move on. Yeah, we're still getting 8, so that's nice. That makes me very happy. Hopefully it makes you very happy as well. And then basically the only thing left to do, I think, is to make this into a bunch of ternaries. Yeah. So we could basically just say at this point, like, because we have if something, then return something, right? If something, return something. If something, return something. So I'm just going to go right for the return, and then we'll just put each of these conditions into our ternaries, individual ternaries. So if it's this, we're going to return accumulator. Otherwise, if it's this, or if this ends up being true, question, we're going to return -1. Otherwise, if it's not that, then we start to ask these kinds of questions. Is the type ACC? Because if it is, we're going to return this thing. Otherwise, we ask ourselves, is the type JMP? Right? Yeah, that's the other thing we ask ourselves. And that might be the last ternary. Yeah, because then we're just going to go right into this math.max thing. And otherwise, it's this math.max thing. You know what? We could probably even make these more efficient too. Wait, where did it go? Is it this? Did I accidentally save this and then it... Oh, no, it's just from the way I pasted it in. Okay, so it should just be that, and that should be it. What I was about to say is we could probably even make this a little more dry in the sense that, like, it's possible it might actually only be this value that we need to change in terms of the found mistake. But no, we need to know which one is... Yeah, I think I'm okay to just keep it like this for now. But if you come up with a more clever strategy, then definitely feel free to leave a comment about it below. Let's go ahead and save that. And yeah, nice. That's looking good, right? I think so. Okay, so let's run that. We expect 8. We get 8. This might be a little drastic, but I think I'm going to go ahead and delete this thing. I'm done with it. Yeah, so we got our instructions. It's a response text. Yeah, okay, good. Then we're just going through the instructions here. We're basically doing that tree traversal thing we were talking about before. It's essentially just another depth first search that we're doing. So this is kind of interesting, you know, because it sort of shows us that like these kinds of things, depth first search, graph problems, tree problems, we might think of these as being kind of like, you know, niche or like very specialized, very like outside of reality, right? Very academic. Whereas it turns out like there are a lot of real world situations that can be modeled pretty accurately using things like graphs, and therefore we can apply search algorithms and stuff like that to them. So this is one of the things I really love about this advent of code. I mean, they keep giving us these great problems that just have so much delicious content beneath the surface, right? They're presenting it to us in a very different way from the way we end up actually solving them. So we can sort of, it's almost like we're mining for gems, right? Anyway, maybe that's a weird analogy. Sorry about that. Let's go ahead and copy this and we'll put it in here. Yeah, we'll just replace these lines with that. And I think that's all of our stuff that we need. Yeah, we'll just console log the run command, and we should be able to just copy all of this, go back to our split screen, open up the browser console, and then paste this all in. And I'm sorry, the font size is very small in the browser. There's probably a way to change that, but okay, great. For a second there, I thought it was giving us an error, but we got a number. We got 2,212. Okay, so that's different from what we got in the previous one. That's probably a good sign, and it's a greater value. So that probably makes sense, because if you think about it, like the 1939, that was a result we were getting when the code was entering an infinite loop, right? Whereas this one, we've fixed the error, so it's actually making it to the end. So it's probably going for a longer time than it was before, which makes sense that the accumulator would be a higher value. So let's submit it. Ah, there it is. We got it. Okay, nice stuff. All right, well, I don't think there's really much else I had to say about this one. As usual, whoops, sorry about that. As usual, congratulations. We've solved another problem here. It was a really exciting one. I thought it was really cool, the vastly different ways we were able to solve this one. So it goes to show you why step 2 is such an important part of the process. Anyway, look forward to seeing you again in the next one. And in the meantime, remember to believe in yourself. Anything's possible. Bye for now.